What I was asked to talk about is kind of our view of cloud native and what are we doing about it and what's the implications to what's an SOC guy doing talking about what's a chip head talking about cloud native and why do we care? To us, cloud native is about, the can't read that screen. For us, cloud native is about, cloud native is an approach to application development. It's not a thing, it's not a place, it's not a cloud. It could be on-prem. It's an approach to developing applications, an approach to scalability and flexibility and scale, observing the applications. It's about speed of application development. It's about mixing of DevOps and microservices and modern deployment tools and managing at scale so that when I need more resources, I can spin up the resource I need. When I don't need the resource I don't need, I can spin it down. But I get that application scalability. So it's a different approach to application development. More importantly, that's the fundamental thing is, it's not about a hardware thing. It's about a different view of life in terms of DevOps and how one deploys enterprise applications. For us as a chip company, though, why do we care? When we look at the workload differences of looking between like the old legacy monolithic applications to the virtual or IaaS, even though that's a delivery mechanism, not a workload. But most of the applications that land in the virtual IaaS world are more legacy, monolithic kind of things that have just been ported over to virtualization. But as you start to get to containers and functions as a service, everything about them changes. And there's a lot of stark differences between those kind of applications. And when we look at it, when we analyze this kind of landscape that's evolving, if you think about the old physical monolithic application, it's a single workload on a single machine. There's high software costs. People want high frequency. They're latency sensitive. The data locality is very high. A lot of, even on a large machine, on a single machine instance, a lot of the data locality is sharing through shared memory. The way people wrote threaded applications was shared variables through memory. So big cores, big caches mattered a lot. And that was kind of the way that legacy monolithic applications, and it was very much a pin and run here. I'm going to deploy this on my mainframe, and it's going to run for the life of the app. Or my tandem computer, go to any big bank, and you'll find a mainframe hidden away somewhere with some large monolithic application they cannot get off. The virtual world started to change that. All right, we have got tens of applications, or maybe hundreds, depending on your scale of enterprise and depending on where your comfort level is. I remember when virtualization first came out, most enterprises were like, I'm never going to go there. I can't trust that. Now it's everybody trusts virtualization. But it drove a different kind of architecture at the SoC level where more moderate core count was accepted. It drove higher memory capacity because now I'm packing in a lot of these large monolithic applications into a larger VM. But the intra-VM locality was what was important, not the VM to VM locality. So I still needed that kind of L3 kind of cache sharing because I was taking old code, moving it over, packing it in on a number of cores. So the L3 still mattered. And it was what I call kind of the allocate and run era. I took a VM cluster, I created a VM, a VM with so many vCPUs, and I popped my application and I populated and ran. Now, as we got into start thinking about containers, though, in kind of the container or CAS or microservices, there's a lot more machines. These are, where high core count kind of matters. You're wanting to pack more in. And they're driving a lot of memory bandwidth, and they're driving a lot of data. They're not driving as much data locality because most of the containers are relatively small compared to a VM. You could have a container that, my favorite is a function in a container in a VM. I love the abstraction levels that we keep creating. But there was more, they were more short-lived, not long-lived like a VM, but containers can spin up and spin down as you need more resources for networking or storage or load balancing or what have you. But they were written as kind of a write once, run anywhere kind of model. So I can take this container application, I package all the libraries that are needed on it, and I wrote it once and I can run it anywhere. Now, containers are great because they can run anywhere because they only know how to talk to each other over TCP/IP. They don't care if you're local or not. They're going to talk. The write once, run anywhere is mostly network chattery, and so it drives some unique I/O challenges. But then when we get to the function era, apologize. When we get to the function era, it's really thousands of functions per machine, mostly free software, very, very high core count, driving ridiculous amounts of memory and I/O, memory bandwidth and locality because they're written that way. But to me, one of the biggest fundamental things is the data locality is down in the weeds. This is, the functions only run very short cycles, so there's very little data locality between functions. And it also has a profound impact on startup time, interference, and the I/O NUMA at the SoC level as you're running these things, spinning things up, running them back and forth, turning them on and off. But it's also a methodology that I like to call write once, run when and where needed. So it's vastly different than a container is mostly running. A function might be something that comes into the cloud that triggers some function that says, take this input, run it through a JPEG engine or a compression tool, and then give me the output. And then that function's dead. It's gone. And so we have to look at it as chip designers and go, well, how does it impact us and why do we care? And when we looked at this, there were actually some profound impacts. At the SoC level, all kinds of new I/O NUMA challenges because these things are spinning up. In the old IaaS case, we could pin stuff to cores and sockets and apps, and we were comfortable with that because it was going to run for months or years. Well, in the container and the function world where it's write once, run when needed, or run anywhere, you can't pin 1,000 things down when 1,000 things are spinning up and then dying. Your ability to pin, your function at the core, at the socket, to the I/O NUMA level goes to crap really quick. And so that was a really profound impact that we saw on kind of the I/O latency and the far bandwidth decreases because it's hard to place things that are very dynamic. It's not very static. And on the function, gets even worse because of that. You're doing a lot of runtime code versus compiled, so the code is inherently a lot slower. You're worried about the startup time. When I have a trigger event come in to do something that needs to provide some f of x, it's how long does it take to get that function up and running? Was it on storage? Had it been paged out to DRAM or to disk? So you've got that. And then at the SoC level, the branch prediction logic actually starts to fall apart. Branch predictors are basically AI engines that learn by running the same code over and over again. Now I've got 1,000 functions running. They all run for a couple milliseconds, and the branch predictors, it's hard to train, right? Training needs data, and it needs repetitive training. So your misprediction rates can increase. And because these things are so memory hogs, you've got 1,000 functions. You don't know which one's going to be a memory bandwidth hog and which one's not. So you got a lot of memory variation going on. And again, you've got this whole kind of interference that can impact the core machine's instructions per clock because I've got all this variation going on, right? It's a very dynamic world in that function world. And so that was one of our findings as we studied, well, what should we do about it? And I'll eventually get to what we did about it at AMD, but that's probably the second half of the talk, not the first part. But this was kind of the analysis and studies that we did that concluded that, we should really go optimize a little bit differently. And what was interesting about this, about the same time that we're doing this, I come across a paper, and I put the links up there, but who is this from? This is from, I think this is from Princeton. So Princeton did a great study, and they put out a paper and a white paper on the architectural implications of function as a service. And you know what? That whole paper basically described everything I just went through. And I was like, well, that's good. At least we both kind of researched it and came to the same conclusion that there are actually real silicon implications on this kind of modern DevOps world on how you would optimize an SoC. If you're in the world of containers and functions and you have very little data locality, why am I paying for a large L3 cache. It's not going to help me any because there's not any thread-to-thread communication. But I found this one interesting because they highlighted a lot of the things. So what did Princeton come out with? They said, oh, they observed up to 35% decrease in IPC due to interference. That's cores, variation in cores colliding with each other. And I'll show you a real result of that in a minute. You know, the memory bandwidth, again, they saw a 6x variation in the memory interface, in the memory pattern. These are unpredictable. They saw the, the branch misprediction went up 20x, in this world. And they saw, this 10x execution time for short functions. So, there's this huge latency of, is my function loaded in memory? Was the operating system or the scheduler or whatever thing I'm using Lambda or Wisp or whatever, did it get it pinned in memory right so they could start fast? And then, so they saw, a slowdown in overall code by many of these things, whether it be interference or the fact that they're mostly running more runtime code and not compiled. But this was an interesting paper to kind of validate some of our internals as well. So I got to give Princeton really good props for an interesting paper in this graphic they put together that talks about a lot of the things that I kind of pointed out. And so for us then, as we think about cloud native, for us, the cloud native market is huge. It's, it's a lot of free software. There's a lot of, if you look at the cloud, the landscape from CNCF, right, there's a gazillion packages and programs and things that are part of the cloud native framework. And so for us being, maximum software compatibility is required. I mean, that is bar none the number one thing that we learned is got to be compatible with a vast ecosystem. And so for us, this is about, and our message to customers is spend time creating the future, not porting the past. You can probably figure out what that one's targeted at, but that's an important thing. Most companies want to do the next big new business thing. They don't want to spend the time porting to get 10%, 20%. When the rest of the world is moving to AI, are they really going to want to port the last thing that was hot 5 years ago? And I think it's a very important realization in our industry about spending the time on the future, not porting the past. So that was an important thing for us. The other observation that we had at AMD was, this whole notion of cloud and cloud native is really driving this new shift in what I call the tenant operator separation. And if you think about the tenant, let me describe the tenant and the operator. If you go to AWS and you take out an instance, you are a tenant. AWS is the operator. They own the OS, the hypervisor, the storage stack, the networking stack, all the services that you as a tenant get to lease or run, they own. And all the clouds and cloud native, they want to shift that thinking from the tenant domain to the operator domain. They want to spend all their innovation dollars on the operator domain so they can have more tenants. So that's been driving a real shift in this whole notion of, domain zero, especially in the hypervisor world, where domain zero is that privileged, it's part of that privileged OS that comes up that's providing all the services. This is where your virtual NICs and virtual networks and all those things are coming from that privileged domain zero. So in the past, we looked like this. So we had VMs that were part of DOM-U. This is where the tenants lived. The operators owned the core hypervisor, the DOM0 services. This was the control point. This is where the networking services and security services and access controls and driver stacks and storage and network service, all that came from that core, this operator level. And then underneath, you had the physical hardware. So they were, trying to virtualize all this, but they were presenting stuff up to all these tenants. But what's happened with this tenant operator separation is this profound shift in driving that control point change between the land of the tenants and the operators. And so the operators want to live down here. They want to live on a data processing unit. They want to write their firmware, their software, their control plane. They want to move it down to the DPU. And so that way, one, they can sell more, put more tenants on that infrastructure. Because in the old world, all those operator services were consuming cores. They were all consuming cores. They were adding different amounts of jitter and determinism. Maybe you have one tenant doing a whole lot of storage, and so that's actually upsetting the whole, the whole server. So they wanted to get all that off so that they could innovate and drive a whole lot of value in this space, because they want to own the code here and not have their code mixed over here. And so that's a big, profound shift that's going on, starting with the biggest cloud vendors and working their way down. Right? This is, the first one probably there was AWS Nitro. This is what Nitro's doing. It's taking all those DOM zero services, virtualizing them, moving on their card in their own domain. And for us, if you kind of look at the definition and then, well, what's a DPU in general? There's a lot of ways to do a data processing unit. Some call them a DPU, some call it a SmartNIC, some call it an IPU, but they all do the same thing. They all have the same functions, essentially. There's different approaches, but a DPU is basically that adapter that offloads those operator processing functions and tasks that a CPU would normally do. And if you kind of look inside of a DPU, they're all more or less the same. Architecturally, they're different, and I think ours is better than everybody else's, by the way, if you didn't know. But they all have, they're providing virtualized services to the host, whether it be an NVMe. I can emulate an NVMe drive. I can emulate NVMe over F. I can emulate, a VMnet. I can emulate NICs. I can emulate that on the DPU. And so I've got, my pathway, I've got some high-speed networking coming in. And normally you have some kind of high-speed programmable accelerator. In our case, it's a whole C of 144 P4 match action engines, which is basically a fancy word for saying we have a highly optimized domain-specific architecture for packet processing. And we have 144 of those little widgets in our Pensando DPU that have an instruction set. It's a complete instruction set in cache, but it's instructions unlike anything you'd see on x86. I mean, it's bit manipulation, bit roll, it's all kinds of bit manipulation. So it's very domain specific. And then you normally have a high-speed interconnect into your CPU domain that's doing that slow path processing. Maybe there's some exceptions that the network, the programmable accelerators, I don't know what to do with this packet, I need to ask somebody else. And so there's some services on security and access controls that you're just not regular running all the time to get offloaded the CPU. And then they generally have some kind of backside I/O where you could attach flash or NVMe or storage class memory to run those different services. And so this is where we're running, network and storage services are being pushed down to here and exposing that to those instances. Again, there's a number of approaches to this and how to go do it. But it's a lot of software. But this is where the operators can innovate, at a major pace, and it provides them, a lot of value add. So it's like, well, why would they go do this? Why would any on-prem, tier 2, tier 1, MDC cloud, why would they go down this path? And, as I've looked at this, it comes down to a number of kind of benefits. The first one that jumps out is I can get more tenant instances. Instead of losing 30% of my cores to running the operator services, I have 30% more tenants that I can sell. So that impacts cost. Less CPU cycles on those operator services, so big cost savings. And depending on which cloud vendor, I would say it averaged anywhere from 15, 20, upwards of 35% were being lost, to the operator services. And this includes VMware. I mean, VMware, when VMware runs, they're an operator. They've got the host, they're running all their operator services. This is why VMware is doing the Project Monterey, to get all those services off. So it could vary anywhere from 15, depending on which cloud, which vendor, and because you can back into the math. If you go to one of the cloud vendors and you look at the largest instance they offer, let's just take, for example, if you go to the cloud and the biggest instance they offer is like, say, 82 cores of an instance, but they're using a 96 core Genoa, you can do the math and figure out how many cores were lost to that operator tax. And so that's what they're trying to move. But so this is a way to get more cost. But a lot of those guys, it's not just about cost. There's a lot of other values. One of the big advantages of this model is creating that more determinism and higher performance. So by getting those functions off that are heavily I/O related, I/O is I/O is the reason we have contact swaps and why we have multi-threading. So we can go do something else while we're waiting for the I/O to complete. So every time you do an I/O network storage, you're creating some determinism, some jitter. And so by offloading that, you can make my instances where my tenants run more deterministic and higher performance. And a part of that argument is the more deterministic that you can make in the cloud, the better you can go make your sales pitch to move enterprise apps to the cloud. Whereas, the enterprise might be on bare metal because I want deterministic performance. Well, I've got to go address it in the cloud with something like this to provide that more deterministic behavior. And doing that is one of these key enablers to fast and microservices, getting those services, because now I'm dealing with thousands and thousands of functions, potentially thousands of interrupts, thousands of storage calls. So I need to be able to offload that. The other part that you gain here is that's important on the cloud and cloud native is that consistent management. How do I enable that complete out-of-band centralized management to the server without disrupting all the tenants? So I've got to be able to come out of band. But that also means I need to be able to do it anywhere in the world. There are many cloud operators and on-prem operators that want to offer it in different locations, or I have Outpost. How does AWS reach into Outpost and control it? First thing you have to assume as an operator is that the tenant's going to screw it up. That's just the way life is. The first thing I do when I get a new PC is I wipe out the hard drive because I don't trust the OEM to install it the way that I would like it. So the first thing I do is wipe it out, get rid of the partition. I don't need a hidden partition to restore it to the state that I was going to wipe. So the first thing I do is format it, wipe all the partitions, install it myself. That's human behavior. But they need that control to be able to reach in and maybe reinstall the OS or update the firmware or whatever it might be because they rented the gear to you. So that enables them that consistent management out of band. It does provide this whole end-to-end security and control. So I created this air gap. The DPU is the only one that can update the firmware, that can update the BIOS, that can update the NIC driver, the whatever have it. There's no more OS in-band control to go update firmware or patch or any of that. It's all in the operator hand now, and that saves them money, right, from screwing up machines. And the last thing that it gains them is really this idea of abstraction. So by emulating these services, they don't care if they plug in an AMD, an ARM, or an Intel. They're providing the same storage, networking, emulated services to those hosts through standard PCIe kind of devices. So they tell the BIOS, I'm an NVMe drive. Here's your boot drive. It doesn't matter, right? So it helps them go faster on delivery of instances because they've abstracted it. So that's an important thing on this whole journey of cloud native is this whole movement towards this tenant operator separation. Now, will enterprise be a big adopter of DPUs and this operator tenant? I don't know. There's a lot of pros if you're making a hybrid cloud on-prem and you want to have a different kind of control path. It certainly brings a lot of value. If you want, some on-prem operators are looking at it from a control management perspective. I can push it closer into the box, and I can push firewall and services like down closer into the DPU. Some are looking at it going, well, if I'm running on, if I'm virtualized and I'm losing 30% of these cores are cheaper, so I can come down on the x86 cores and put in a DPU. So there's a lot of different TCO angles you can take that make it, but it's certainly not here to tell you that everybody's going to be adopting a DPU in the future. But it certainly is one of the options to change your TCO model and think about it differently. And so for us then thinking about, well, how does this cloud native, again, talk to the principles of SoC design? And I found this the other day, and this might be a little stretch. I might be stretching it a bit. But as I read through the 4 key principles of cloud native, and if you think about microservices is an approach to take a building block approach to build your app. Well, that sounds like chiplets. That sounds like what we're doing with CCDs and IODs. It's a modular approach to building a chip. Containerization talks about the ability to mix and match different libraries and runtimes into a container so that I never screw up my app always has the version that I built it with. Well, that kind of sounds like mix and match, kind of what we did in Zen 4. The whole continuous delivery is this whole notion of taking one design and continually evolve it over time and make it better and better and better. Well, if you look at our 4th gen Epic, we delivered 4 different unique optimizations off the same building blocks. That sounds like continuous delivery to me. It didn't come out at the same launch. So, we continuously rolled out the 4th gen Epic. And then, the DevOps is a method of being able to design and architect and promote standard kind of communication between your different blocks. And for us, at least, that's Infinity Fabric. That's what enables us to mix and match so quickly. So I looked at this and said, hey, our chip is cloud native. We didn't know it yet, and we haven't marketed it yet, but before we even did the other stuff, we followed the cloud native principles to come up with this. It might be a stretch of an argument, I understand, but I'm making it here. And so, getting then into the chiplets, our approach and how this helped us. If you kind of look at the old school, you look at your big wafer and you look at your monolithic dies on top and your little bitty chiplets on the bottom. How does this approach help us go faster and accelerate past, Moore's law? And if you kind of just, the math of this is pretty simple. It's, if you have a big wafer and you have a bunch of big monolithic dies, you get a certain amount of yield. You get more yields of smaller chiplets. So you get more functional SoCs out of chiplets than you do monolithic. That's the basic math behind the chiplet approach, is that we can get ability to mix and match at a finer grain level than we could with a monolithic design. But it also enables, because of the test manufacturing yield, we're able to drive, we're able to mix and match our chiplets with different process nodes. The chiplets in AMD are not the same node process. We mix nodes from different foundries at different geometries because the I/O world generally likes bigger SerDes and more power and more analog. And so that's generally in a higher node process than our CCDs. And so when we plot this out, versus a hypothetical monolithic, we have a much better price model in terms of cost model, but it allows us to have a much different pricing model because our cost, it's pretty linear, right? It's my chiplet, my IO die costs so much, my CCD costs so much, I put so many down, I get X, Y, and Z. I'm not searching for the Easter bunny to get the perfect core yielding device in a monolithic. And so that's a big plus for us. And it's really one of the things that I'll argue that how we helped extend or starve off or extend Moore's law. Because if you think about where we were in the industry in terms of a monolithic die approach, you only had so much silicon area. And there's a reticle limit when you go to TSMC or a package, you hit a reticle limit of I can only build a monolithic die so big. The bigger, mainly they'll let you build it bigger, but your yields just go down really bad. But there's a reticle limit. And so if you're on the normal path of Moore's law, you're kind of, well, my silicon area is kind of fixed on the package and the reticle limit. So I get more transistors every year. So maybe I can do a little bit more. But I think that's played out on the other side of the camp that was doing very monolithic, where they were stuck at 22, 28 cores for a long, long time. And then they finally got to 40. But they were hitting the reticle limit of how did they break free? And so with us, we were able to go to multi-chip modules. So if you look, we were able to put more silicon area in the package. And did we change the fundamentals of Moore's law, or did we extend it because we're fundamentally able to put more silicon in the package than the competition? And so we were able to put more chiplets in as you look out in time at 2.5 and 3D hybrid, we're talking about 2,300 square millimeters of silicon can go in to keep advancing the business. Moore's law is an economic law, right? I can build a chip that costs X and it'll be valuable enough people will pay me Y. If they won't pay me Y, Moore's law is dead. But we're on that train, and by extending the approach with the chiplets, we're able to change that curve and get more silicon in to add more value. And so the other part of the cloud and cloud native that's important for me to think about as I look at this as a architect and strategist at AMD is this. There was a great blog. I'm not sure who did it, but you can reference it here if you can type all that down. I'll send it to you. But it was a great blog on how many lines of code have been written in the past 20 years. And so I've termed this the 3T problem because he came up with a mathematical formula that said there's so many computer science engineers, they write so many lines of code a year, blah, blah, blah. And he came up with this 2.781 million lines of code written in the last 20 years, 5x more than the number of stars in the galaxy. So that's a lot of code. That's a lot of code. That's a lot of legacy. And so porting, getting it recompiled is easy, relatively speaking. But actually testing, tuning, validating the Q&A and all of that is hard. And it takes time and money with an unproven ROI at the end of the day. And so what we're hearing from most of our customers, like I said earlier, is they want to keep the legacy alive while they invent the future. No one wants to go back and rewrite the old code. And so for us, this is a fundamental thing on why we're on the path we're on with core scaling. And so, this is very challenging for most users, most enterprises. There's some companies in the world that have thousands and thousands of engineers, and yep, they can go port. And a lot of those guys are spending their time porting to the operator part of the new problem. And so again, for us, it's about create the future, don't port the past. And so, for AMD, what this means from a product standpoint is looking at, well, how do we make silicon that's better for all of this? And so one of the reasons we acquired Pensando, hopefully I told you enough about DPUs and convinced you enough that, hey, DPUs matter. They matter in the cloud, they matter in cloud native, which is why we acquired Pensando, which was, we think, the best DPU on the market in volume production. And so we're able to take EPYC and Pensando, and we've got a lot of big wins from Oracle. These are all public, from Oracle, Azure, IBM Cloud, VMware, and there's a lot more. But we introduced a Pensando DSC, a distributed services card, that basically does all those services that I talked about earlier. They're running on this ARM core and this 144 match action engines that are part of the Pensando architecture. And these devices are really interesting because they're architecturally, it's just an advanced SoC, but they're very different when you look inside. Well, I'm sorry, I don't have a block diagram. I meant this to be a block, but when you look inside, like I said, there's an ARM core subsystem tied to a high-performant memory system. You have these match action engines, or P4 engines in our case, that are domain-specific for the networking and storage world. You have encryption, you have compression, you have lots of other kind of accelerator features are in the DPU. And that's really a profound thing for us as we see, and this is why our strategy on core scaling is different than the other guys. We see the world that's evolving between the operator and the tenant. The operators are moving their code to the DPU. I have to be very, very smart and judicious about what do I leave on the tenant side, because if it's on the tenant side, the operators can't use it. If you put a bunch of compression, encryption, and stuff, whatever, on the CPU side, but they've moved all their value-added code to the DPU, they can't use that. It's just dead silicon. So our strategy at AMD is focused around giving a lot of good cores, being very judicious about what accelerators we put in, but optimizing the operator side with all the accelerators they really need. This is why in
Rob,
the Pensando,
isn't there an argument that if you put the accelerators on that tenant side in the CPU, then tenants have the ability to do stuff that on their end on the user workload that the operator isn't, like advanced encryption for authentication, application acceleration. So kind of getting this differentiation at the CPU-based accelerator. All at some point, a core is a core is a core,
right?
From a tenant solution. And now I differentiate at that consumption model?
Yeah, no, I agree. There are some tenants that will make the software investment to maybe they don't like, if you think about a DPU and the storage compression, it's inline compression and encryption on the network and storage. So that's already there. So if the tenant wants to do some unique compression or some special encryption, that they're free to do that on the CPU side. But to use the problem that we see on that side is operators will port code, tenants generally do not. And so to port to the advanced accelerators on the CPU side, it's a long hurdle, right? There's no drop-in code, there's no free lunch. The tenants are going to have to write that code. I don't just get it for free. If I use the compression and encryption that's coming in line from the DPU, the operators have abstracted away. You don't even know as a tenant.
So
you're getting compressed storage.
I would argue, I don't know if I would agree with that. So as folks like AMD are working with projects that take advantage of EPYC 4 accelerator, if this stuff is natively part of either the Linux kernel or sidecars or even other projects, then as a developer, I get the advantage of that acceleration without knowing anything about the low level acceleration.
Yeah, no, I don't disagree. If projects do it and if people port to it and optimize for it, certainly can. I'm not saying that is not possible. I'm just saying that's not the normal case. It's not the volume case of the tenant behavior. Most people that are wanting to use a database want to use the in the box, the GitHub version of the database. They don't want to take that and then install someone else's special library that changes the database behavior, whether it be an FPGA accelerator or an NCPU accelerator. Oftentimes it takes a special version or a modification of the standard application. Now, if standard applications were to completely adopt it in the box, the problem is you can't count on it to be there, right? I mean, the other guys have a whole complex menu of, I get this here, not there, here, there. So you don't know what accelerators you're going to get with the other guys. So, but I do agree with you. I mean, if people do it, if it has intrinsic high value, then yeah, sure, it makes sense. I'll give you one way of an example of a discussion I had recently in Europe with a customer. And I asked the customer, I would love to have this discussion with y'all, to AMX or to not AMX? So the discussion we had was, on your AI inference, do you want to do CPU only, CPU plus AMX, or CPU plus GPU? And the most profound answer that I had, which was very intriguing because I hadn't processed it, but I'm a good listener sometimes, not according to my wife, but sometimes. But what the customer said was this. He said, look, both CPUs and GPUs are very expensive, and they're optimized for their own domain, for their own world. And they said, and they used the example of Sapphire AMX and said, list price, arc.intel.com, $17,000, $283, a core, and it equates to, 4 tops per core. That equates to $71 a top, was their quick math, if you kind of follow that progression. And they said on the GPU, NVIDIA's GPU is $30,000, delivers 4,000 tops. It's $7 a top versus 83. And the guy said, the more AMX I use, the more servers I must buy and deploy. So I'd rather deploy a GPU and use it when I need it instead of having that tax setting there for when I'm not, was their kind of logical argument. And so to me, if you're going to integrate, it's got to have that huge ROI. So having something that's a 9x ROI negative, that core is really expensive. I can go get cheaper tops somewhere else. So that was their argument, which was...
I kind of understand the argument, but I think if we're talking about the mass market, most of us are going to be using LLMs that are tuned to 1 billion parameters versus LLMs that are tuned to 1 trillion parameters. So at some point, the return on GPUs, or even needing to wait on GPU availability to get that return, won't be worth the lost business value. I got to wait to both AMD's and Intel's advantage today. I have to wait 42 to 48 weeks to get a H100.
Right.
I can get Intel and Epics today
Yeah.
across a whole lot of clouds
Right.
with built-in accelerators. So there is, this isn't as simple as saying, well, how much is a top per platform versus how do I make $1 million
Yeah.
off of the compute that's available to me now?
Yeah. No, I agree. Yeah. No, there's an availability. And so if you look at you then narrow it down further and say, Genoa, roughly speaking, I think it's 0.8, 0.88. I don't know, call it one top just for easy math. Sapphire is 4 per core. So it's 3x, it's 4x delta. If you've done any end-to-end AI, if all you measure is matrix multiply, yes, you get a 4x advantage. If you look at the end-to-end AI, the totality of I have an input, I've got to normalize it, I've got to load a model, I've got to do something, then I finally load a model, do some math, get an output, do some business logic, decide what to do. What you end up finding up is you sped up 10% of the problem by 4x, which equates to a 1.1x something speed up overall, which is why on like TPCX AI, when we benchmark Genoa versus the best of the other guys with AMX on TPCX AI, we win by 1.9x. That's because the matrix multiply is such a small part of the problem, it doesn't help enough. It's Amdahl's law in practice, right? If I speed up the smallest part of the problem, I don't speed up the entire problem. So I do agree there's going to be a place and a time, but I think for what we're seeing right now is, CPU AI for inference is perfectly fine when you understand your application and you understand the real end-to-end, you quickly get to the realization that speeding up that little bit of the code by 4x didn't provide any value.
Well, looking at, I guess, the market approach and like who the actual addressable market is to get these optimizations, you're starting at hyperscaler down. The average consumer that writes pretty piss poor code that ChatGPT is going to poop out is not likely going to get, a 4x advantage.
Right.
So there's an interesting thing of, are we creating optimized applications that can actually leverage making the jump, or are we going to, as IT operators who have incredibly high pain tolerance, keep mushing through with bad performance on the current available chips and then just hope that the price goes down rapidly to make it a reason to jump?
Well, we hope to add some, competitive chips to the market here real soon that we hope will change the game. But I do think, that from a CPU inference, for the vast majority of customers, CPU inference is completely adequate for what they're doing. And when you look at the end-to-end speed up, and then it works everywhere, right? The moment you go down a certain path, if you go down the AMX path, you just checked into Hotel California, right? You just eliminated your choice.
It's a really big hotel, though.
It's a hotel, it's a hotel, but it is a path. But now here's the question for you as a counter. If you looked at the latest Intel client news, they announced they're putting a neural network processor in client. Why did they do that? Because they can't meet the TOPS requirements required for the operating system. So they're having to put a dedicated accelerator, which means they're not going to be using AMX because they can't hit the performance levels. So I don't know what that means for the future. I'll let you guys speculate and write about that. But I find that an interesting observation that the client guys announced a new path for AI that is not, I'm not saying they said they're getting rid of AMX, but they did announce their new path for AI and client is an NPU, which is not. So that begs the question a lot. But I'll also get into, in a moment, there's a profound difference on accelerators that I think people, that we need to fully understand. So I'm going to skip the epic journey. Hopefully you're all very familiar with the epic journey of Gen 1, Gen 2, 3, 4th generation. We did 4 versions of Genoa, Bergamo, being our cloud native, large cache Genoa X, and recently the Sienna to round out the Zen 4 platform. Thinking about the impact of how SoCs are designed and the different approaches. If you take our approach on the left, we have a central I/O die and a bunch of CCD cores. So we have a centralized pool of memory. So all our memory is managed by the I/O die, and everything is managed there. If you come over to the other world of tiles, It's basically a distributed pool of memory. Each tile has a little bit I/O and a little bit of memory. So that means if I'm driving maximum bandwidth and interleaving across all channels, I've got to fight my way across all of those chips, which has a profound impact. And the other thing to note that I don't think I included the graphic in here is the GPU. If you think about a GPU versus a CPU, these are different optimization points. So if you take our Genoa at 12 channels at 72 bits, it's about 768 bits wide of memory. And we're at about 460, 500 gigabytes a second of socket, but we have thousands of gigabytes of memory. If you look at a GPU, take a GPU that has 8 stacks of HBM. Each HBM stack is 1024 bits. The memory width inside the SoC is 8,192 bits. It's 6.5 terabytes in package memory versus 460 gig. So drastically, 10x, 15x, difference between width and bandwidth. And so the point being is CPUs are optimized for cores, and when you start to throw in other sundry things, you can throw the balance of that SoC off greatly. And so when I did this chart, which is a theoretical calculation of, if you just take the amount of bandwidth we have and core and plot it out, you get this nice, pretty theoretical graph. We start with more memory because we have 12 channels. They both have 8. But if you plot it out, at 60 cores, using Intel as a reference, 60 cores, we've got 2.6 gig more of bandwidth per core. It makes sense. We have 50% more bandwidth. And so that means all the way out to 90 cores, we can deliver the same bandwidth as they can at 60. And the math is easy, 60% or 50% more cores, so 60 to 90, math's easy. But what's interesting is then now, this is theoretical. So we went and did some testing to figure out, we talked about interference, noisy neighbors, we're worried about accelerators consuming bandwidth. So what happens in a real world? So what we did here was we took Bergamo, core 0, and we ran stream triad on it. And so this red line is stream triad. That's all we're plotting. That's core zeros, memory bandwidth at core 0. And then we introduced noisy neighbors, another copy of stream triad on core 127, 126, 125, all the way down to next thing you know, you got 128 of these things running. But I'm only plotting core 0. I want to know what happens to core 0. And if you look at AMD's, we have actually, because of our centralized pool of memory, we actually have a very nice linear decay down to where, the cliff kind of hits, and then we fall off. All the way out to, this is all 128 cores running that. But again, we're only plotting core 0. Now, if you look at the other guys that are doing more of a distributed pool of memory, they start lower, but we have more memory bandwidth. That's a given, but why they should be higher, I think, anyway. But if you look at the shape of their curves, you can see what I mean by the noisy neighbor impact. I mean, after about 20, 24 cores, there's really no bandwidth left. I mean, depending on where you like to draw your line on the knee of the curve, where you're comfortable at. But this is the impact of a noisy neighbor being a core. Now, imagine if your noisy neighbor is a compression engine or an AMX engine, whose sole goal in life is to stream things in and out of memory as fast as possible and hope I don't interrupt everybody else that's trying to do work. So this is why for us, being very judicious in our SoC architecture, very judicious in what we decide to put in. I mean, we could put a, go crazy. We could put a GPU in Instinct, but it would just suck the bandwidth out of the memory subsystem because we're talking about drastically different SoC optimizations. Again, EPYC about, call it 500 gig a socket. And Instinct's going to have 6 point something terabytes.
So do you have data around, since this is cloud field day, do you have data around like Graviton 3 in comparison? Because Ampere is kind of like,
Yeah, so we can only get, we should go do that. We do have access. I don't expect it to be drastically different, to be honest. But I don't know on Graviton. This is the Ampere Ultra 128. So as I said, it's an older device. It's DDR4, but but this is the reality of what it looks like. And so the point here is, the theoretical was supposed to be 2.5x at 60 cores, but at 60 cores is actually 6x difference. And so my cautionary tell to customers with anybody using an accelerator in the CPU, be careful, because those things are memory compression engines are bandwidth hogs. AMX can be a bandwidth hog. That's what they're intended to do, right? They're supposed to grab stuff from memory, do something, and push it back. And so this was an easy way to kind of demonstrate the noisy neighbor of what could happen. Now, we've done some interesting stuff because we care about high core count scaling. We care about customers being able to adopt high core counts. And so we've been working on some technology that we call PQoS that's in our parts today. It stands for Platform Quality of Service, to where you can set up classes of service. I can set up a number of classes of service. I can assign threads and cores to it. I can limit how much cache, how much memory bandwidth. And so what we did here was we ran the same test again. So except we changed the color on Pergamo to green for some reason. But what we did on all those noisy neighbors is we limited them to a 50% PQoS. So we said, you only get 50% of what you could. And so you can see the artifact of that is being able to protect core 0 and keeping, so we kept core 0 up over, 30 gigabytes a second throughout this whole test. Now, the point on all that is, as an operator, the ability to go in and have different value instances. Maybe you have cheap instances, you just want to, maybe you just want to give them 1 gigabyte a second per core. Today, if you look at the cloud, you can buy the number of cores, how much storage, how much memory, how many IOPS, and what network bandwidth. This could be a net new knob which says, well, how much memory bandwidth do you want to give them? It also could allow the cloud market to actually play memory Tetris. If you look at my operational fleet, see how many cores are available in my instances, see how much memory bandwidth is left, and maybe I'll go to do some spot pricing and create some special instances because that's what's only available in that server. And so this is to me, is a really unique and new lever that we can pull to help customers get to that confidence level of high core count. And so we have to be able to provide quality of service within the socket and within the platform to help customers get over that. But what I wanted to just talk about is, the generations of Epic that we did and the optimizations that enabled with our design. So we started out with Genoa, a balanced, very balanced platform, very balanced core platform from a density, IPC, frequency, efficiency. We came along the idea that, hey, I could go, for this cloud native market, I can trade off a little bit of frequency, get a little bit better power efficiency, trade off some things, and I can get to a much higher core density. Same RTL, different physical point, on the VF curve. And then we said, with Genoa-X, we said, hey, I can take these base building blocks, I can stack a large L3 cache and go create this innovative new product for technical computing, simulation, and those markets. And that's how we got the first 3 parts of the Zen 4 family. And then the last part that we introduced was the Sienna, where we looked at it a little differently from an embedded form factor edge telco space, where one of the more sensitive metrics was really that the TCO is a little different, where it's like perf per watt per dollar, perf per dollar, perf per watt per dollar. Everything had a little different slide. And so with Sienna, we really optimized around that perf per watt per dollar by making a smaller package, less DDR channels. We were able to get the platform costs down, but we're leveraging the same building block. And that's how we were able to dial in Sienna. But if you look at, the difference between the Zen 4 core, which is our classic core, and the C, which is the compact, now there's a profound difference in size. So, every millimeter matters in a chip. And so, there's a pretty substantial millimeter area difference. They're both NTSMC5. It's the same RTL, the different physical implementation. We reduced the cache because cloud native doesn't care about the size of the L3 cache because of the data locality. And so we optimized the physical design on this red curve where we start it at a lower power per core and we limited how far up that by lowering where we started from a power per core, it limited how far up we could go frequency. I mean, that's the physical trade-offs that you make in any foundry process is if I'm willing to spend money on big, powerful transistors, I can have high frequency. If I want to have more efficiency, I've got to start at the other end of the curve, but I'm going to sacrifice that top line frequency. And so this is, kind of an illustrative purpose on the different characteristics at the manufacturer, at the physical design level that enabled us to go do that. So I'm going to skip the product stuff. We can give you this all day long, but I did want to get into the efficiency curves on all of this because it's actually pretty profound, and we always like to use public verifiable benchmarks in our work. Sorry. And so oftentimes we look at spec power and we look at the result and the spec power score and everything looks so good. To me, it's always important to look at the shape of the graph of power efficiency. And if you're not used to these graphs, this is straight off of Spec Power's website. But if you look at this, basically this saying at 10% load, I'm delivering this many SSJ ops per watt, at this, the blue bar being the power. And you can see, we're at like 34,000 SSJ ops per watt at the overall spec power score. But what's intriguing about this is if you look at, our, idle active power 126 versus theirs 153, and we've got considerably more cores, right? So we're active idle, we're less than the comp. But then if you look somewhere else, if you look at like their 100% load, they're delivering 14 million SSJ ops. That's basically the Genoa at half stride. That's 50% on Genoa to deliver the same amount of SSJ ops, which is why we have such a stellar spec power score. And if you look at compared to the best published score from the ARM camp, again, looking at the 9754, we're idling at 126, and their actually idle is higher than ours. This is the best published score on spec power that they've ever achieved, which is 143 versus 126. Now, we all know spec power is a little bit game. Everybody optimizes a thin config, but that's fair because everybody optimizes a thin config. But if you look at this, you're comparing, idle, we're less. But if you look at their top load, they're at 5 million SSJ ops. For Genoa, we're at 20% load. We're at 20% load to deliver what this thing can do at 100% load. That's why we have such a huge power efficiency. And the other thing that's interesting that I missed to pointing out here is if you look at these curves, it kind of tells you how hard people are pushing the silicon. So you can see ours goes up pretty linear. We're about 80, 90% at max perf per watt. We push the power a little bit, we come back. If you look at Sapphire, their maximum efficiency is at 50% because they're pushing the power so hard to get whatever frequency they can to be more competitive on the spec end. So it really impacts that overall shape. Now, Ampere's they've done a really good job. They're very linear in their perf per watt going all the way up. They did not push we pushed on ours. We pushed a little bit. They did a really nice job, I would say, on driving that linearity.
Yeah, I think at the end of the day, if I'm a cloud tenant and I'm watching this, what's the walk away? Like, what am I when I go to my AWS console, and do I now go to look for AMD powered instances? Like, what's the bottom line?
Yeah, so at the cloud level, the bottom line is pretty easy. You're getting more performance per dollar with AMD instances than the competition. You're helping the earth by using more power efficient architecture. So you're helping your sustainability go versus standing it up in something else. And with AMD, you get the full x86 compatibility of those 3 trillion lines of code that have already been written and tested. So you get that compatibility. And then if you look at, one of the last things, if you look at our journey in terms of Zen 1, 2, 3, 4, the execution excellence that AMD has been on, it's kind of unheard of in the industry, the way we've executed on generation to generation to generation. When I sit down with customers and I talk about our roadmap, the feedback that I often get is, Robert, y'all's roadmap is boring. Nothing's changed. You're doing exactly what you told us 6 months ago, what you told us 12 months ago. So your roadmap is boring. That's the best compliment I think we can get as a company when our customers tell us our execution is so on track that it's boring. And so that's why if you look at some of the biggest supercomputers, some of the biggest, most challenging problems in the world, whether it be winning in Tesla or Frontier or the El Capitan machine that's being built, they chose AMD for a reason. They had to be able to hit these milestones in terms of performance within a power envelope on schedule, at Frontier. El Capitan is in the same boat. That'll be the world's first second exascale. Will be the world's first 2 exascale machine is Frontier. And again, people are making long-term. They made this decision, several years ago to commit to our roadmap because of our execution. So I think to me, those are the biggies, the innovation that we bring, the pace of innovation, the performance per dollar, being good stewards of energy. By far, we are the leaders of the best stewards of energy on the planet. And if I take away from some of the mega themes at the OCP keynotes from yesterday, just about everybody that did a keynote said, AI is going to suck down every joule that we can create on the planet. Where am I going to get the power? Where am I going to get the energy? Where am I going to get the data centers? If you look at the world capacity right now on data center vacancy rates, it's less than 3%, which is like really bad. If you're looking for, I talked to one data center operator the other day, they have 1 to 3 megawatts scattered across 3 locations between now and the end of 24. That's it. And they've got multiple data centers coming online, but the capacity's already been bought. So if you're trying to do an AI project, where do you go? And, we had a keynote at OCP that Forrest did. They did a great job, which they said, yeah, we see the same problem to directory for AI. We've got a solution today. We don't just have a solution waiting in the future. We have a solution today. You can consolidate your data center, 5-year-old equipment, 5, 6, 8 to 1. You can create space, power to go do your new AI business objective. And that's a powerful message right now with our customers as they look at these AI projects and where am I going to go? Where am I going to put it? Where am I going to get the power space within my own data center? It's a power. Data centers take time to build. They don't stand up. Fabs take 5 years to build? I think data centers take about 2. So being able to consolidate is a great message. So I think that's kind of the 5th thing maybe, Keith, on why AMD, I can consolidate down so much more to create space and capacity to go create my AI business disruption without having to port code. I don't know, do you buy that?
So I'll just dictate pretty quickly from hearing that answer. I could say the exact same thing to hyperscalers, not necessarily to the tenants, but to the operators, right? Because the tenants have to deal with whatever the operators grant them access to,
Yeah.
right? So your story works perfectly well. I'm just trying to figure out the audience of who the customer is that you're referring to.
Yeah, no, I think it actually applies to both the on-prem kind of customer that's landlocked. But if you think about the hyperscalers, they're not in an unforeseen problem, right? They have the same bounds of what they have built, what they had forecast to build, and how do they pack their tenants into less space so they can deploy more AI in their existing data centers.
Sure,
sure, they're going to go build new ones, and they can probably build them faster than everybody else, but they're still in that same problem of how do they go stand it up, and how do they create the space and capacity. And so instead of having tenants spread across umpteen racks and servers, if they can consolidate it down, they can now go deploy, their ours or the competitions or their own, AI. So I think it resonates with the cloud operators as well.
Yeah, if you're in a hybrid environment where you have to be both an operator and a tenant at times, and you need to switch, there's no doubt that if I have 5-year-old gear, anything that I buy today from anybody will improve upon it and lessen my problems around, especially power and cooling.
Mm-hmm.
the ability, DHH, with what they've done with re-platforming their platform onto AMD and Dell servers, show that they've saved $1 million already, and they have a cloud-like operating model. So I think that argument, stands up.
Yeah, no, I would agree. I've heard that from. I mean, there's always exceptions to every rule, and they're going to find. But I think the general approach that we're in, the path we're on, is very powerful for that. Create capacity to go do your next new business disruption, and it at least appears to me that everything in the world is going to be better or saved by AI, as best I can tell, based on all the marketing. What was the latest one I saw? What was the Coke? Coke did a version of Coke that was AI inspired.
Yep.
That's creative marketing. You get AI on a can of Coke.
What fantastic protocol is going to interconnect all of these memory and CPU devices, Robert? Is AMD working on anything fantastic that we may have a podcast by Tech Field Day about?
Yeah, I heard there's this little group of consortium of companies working on something called Ultra Ethernet that has been making great strides. That was announced earlier this summer. Open membership has come out. And in fact, at the OCP Summit, OCP and Ultra Ethernet signed a collaboration MOU between OCP and Ultra Ethernet to collaborate together on advancing Ultra Ethernet. So the market has spoken pretty big on the need for advancing Ethernet as the next generation fabric for AI and HPC. And the momentum is great. I mean, there's I think we had 9 members, about 9 founding members, and I can't disclose all. There's been a lot of, let's just say the pace of people signing up is quite fast.